Hello, everyone. Welcome to the Falling Wall Circle Table, Quantum Computing in the Nisq Era, Competition or Cooperation. I'm Julia Georgescu. I'm the Chief Editor of Nature Reviews Physics, and I'm here with three very interesting people. Ina Schiffendecker, who is the head of the Department of Research and Innovation and Digitization of the Federal Ministry of Education and Research. She has worked in academia for many years and was involved in several spin-off companies. Also here with us is Hartmut Neven, who is the engineering director at Google. He is the founder and manager of the Quantum Artificial Intelligence Lab. With a background in computer vision and AI, he's also the co-founder of the Google Glass project. And Tommaso Calarco is the director of the Institute for Quantum Control at the Forschungszentrum in Jülich, and he's also the chairman of the Quantum Community Network. In 2016, he wrote the Quantum Manifesto, which played a crucial role in the creation of the Quantum Flagship Initiative. So without further ado, I would want to dive into this 1-hour session. Just a couple of housekeeping points. There's an audience whom unfortunately we cannot see, but we know you're there and we hope you enjoy this session. Please engage with us by using the chat function, sending us questions. I will leave them some 10-15 minutes at the end to take your questions, but I can't promise I will take all of them. We're aiming to wrap up like about 5 minutes before the hour, so we have some 45 minutes for the discussion and then for your questions. Because I will assume that all of you know what a quantum computer is. If not, you can just Google it straight away. I'd like to start with defining another word that may be not that obvious in the title of this session, and that is Nisq. And I'd like to ask Tommaso to explain to all of us what Nisq is.
So the Q in Nisq is quantum, so we are not going to re-explain that, but the NIS means noisy intermediate scale. So noisy means, handling a qubit or many qubits, as, for instance, Google Teams did wonderfully and is doing wonderfully with the milestone result, which they had 1 year ago. It's difficult because there is noise, there is interaction with the environment, and so handling a qubit and keeping it with quantum coherence, which is what is needed for it to work properly, is something which is much more difficult than keeping a snowball in the middle of hell. There is a lot of perturbance, a lot of disturbance, and this is bringing errors. When I want to use my quantum system for making computations, then this induces errors. So noisy means it's not good, it's not perfect. I have a certain error probability. I could, in principle, correct for it. I could have a fault-tolerant quantum computer, but for this, I would need many, many, many qubits to encode it redundantly. So where are we today? The state of the art, for instance, is given by machines such as Google's quantum processor, which has 53 qubits, probably more. In the meantime, 53 was with the milestone demonstration they had 1 year ago. And this is this intermediate size. So the question is, before we get to the 100,000s or maybe millions, which are necessary to have a full fault-tolerant quantum computer, what are we going to do if we have only a few quantum bits and they are noisy? Can we do something useful? Can we do something interesting? Well, for sure, something very interesting and very exciting. Google showed it, as well as on many other labs around the world. but can we really do something useful for society? And can anyone do this alone by themselves? Or do we really need to cooperate with each other to win this challenge? I like to quote Hartmut Neven when we speak about this, when he says, I don't do this only when he is present, like today, but I like to quote that he says, it's not like, you know, a race between different countries, like space race or different companies. It's rather a race of mankind against nature to tame quantum machines. So this is where we are. Do we need cooperation or competition to win this challenge with few qubits with a lot of noise?
Thank you, Tommaso. Hartmut, can you explain to us what quantum supremacy is? Because your team achieved quantum supremacy last year, and there was a lot of discussion in the press and in the community about it. Can you briefly tell us about the result and what it means?
Yes, I would be most happy to. So why are people interested in quantum computers in the first place? It's because they're expected, or from strong theory, we know that for certain computational tasks, they will be faster, not just a little bit faster, but exponentially faster for certain computational challenges. And that comes because a quantum computer, actually, we all know computers get faster and faster all the time, or at least they used to when Moore's law was still strong. And they got faster because the clock cycles got faster. We got more transistors crammed on a chip. So ultimately, each individual step in an algorithm could be executed quicker and quicker. Quantum computers actually do not necessarily draw their power from there. The individual steps in an algorithm on a quantum computer can even be slower than those on a classical computer. But for certain tasks, we get away with many fewer steps. That's where quantum computers get their advantage from. So, of course, eventually want to show in sort of computational horse race that, yes, a quantum computer makes good on this promise. And this experiment that we conducted last year essentially for the first time showed it, that if you do a computational horse race between a classical computer, and we chose at that time the fastest supercomputer in the world, which was Summit at Oak Ridge National Lab. And then we had a quantum processor in our hardware labs in Santa Barbara, was called Sycamore. And then I often like to picture it like a game show. You write down a computational task, or you write it down twice, put it into envelopes, you give it to the classical computer, Summit, you give it to Sycamore, and then you see which machine finishes the task quicker. And at the time, Sycamore was able to do it in 200 seconds, but Summit, and we never finished the computation, of course, we only started it and then extrapolated, would have taken 10,000 years to finish this task. So this is the essence of the quantum supremacy experiment. We decided since then, because supremacy has unfortunate political connotations, we now refer to this as demonstration of beyond classical computational abilities.
I see. I will come back to both Nisq and quantum computational advantage in a bit, but before that, I would like to ask Ina a question. So I know Ina is interested in how networking technologies can contribute to the digital transformation of society. And from that point of view, I want to know, what are your expectations that quantum computer can do for society?
Good question. Thank you for this question. So, in fact, I would compliment Hartmut's saying about that we know in theory what we can expect from a quantum computer if it's going to work. So, in fact, we mathematically can identify or characterize the class of problems that quantum computer will be able to solve. And these are, in fact, quite a number of interesting optimization problems, which we face in every routing question or other optimization areas. So it is a class of problems that traditional computers nowadays need years or 10,000 years, as he said, to solve. So these are questions about interesting models in the climate area. So how do we manage the climate transition, the transformation, how we solve other problems in the sustainability area, how we solve material questions, how we solve pharma research problems, and so on and so forth. So quite relevant problems that will be solvable once we have a quantum computer.
I see. So actually, this is a question that I thank you for actually laying the ground for this question. So I would like to know, what does, okay, I'll call it quantum supremacy again. I'm sorry for that. I think it's how it's mostly known. Although, yeah, I agree, this is not the best way, the best word for it. How is it meaningful practically? So if you have a pragmatic mindset, you'd say, like, look, I'm thinking of classical supercomputers, and you have milestones like petascale or exascale. And I know, like, if I reach exascale, I have like a very good reasons to think that at exascale, I'll be able to do climate modeling with kilometer scale resolution. So this is one of the big problems that Ina has just mentioned that has very big consequences for the world we live in, and is something we want to do. Okay, so I know exascale, I can do this climate modeling, but like, what does quantum supremacy mean in terms of practical applications? Because the very problem that was used to show the result is not a practical problem. Can you please comment on that, Hartmut?
Yeah, I think the original answer to the question you just asked came from Richard Feynman, the famous physicist. He realized actually a part of his career was dedicated to running what today we would call a data center. And he realized that certain tasks he was interested in, like computing the configuration of a molecule, that because how the equations of quantum mechanics are structured, he will never be able to properly solve this. No exa, no petascale computer would ever be able to do this. And he coins this phrase, nature is not classical, damn it. And if you want to make a simulation of nature, you better make the simulator quantum mechanical. And yeah, this was the original insight that no, it's classical computers are just not good enough to model certain quantum mechanical phenomena. And they're actually pretty prevalent in many disciplines of engineering. Let's say you want to make industrial catalysts to do nitrogen fixation better. This is an example we often give. This is the Haber-Bosch process to make fertilizers. Today, it eats a little bit more than 2% of the world energy production is devoted to nitrogen fixation. And this is because we have to do it at high pressure and high temperatures. But there are bacteria who know how to do it at room temperature with just one atmosphere of pressure. They have a catalytic trick, but we don't understand this trick yet. And we hope that a quantum computer could deliver us the insight. How do the bacteria do it? And then we replicate it on an industrial scale, and it would be a very nice application.
I see. So that leads me to asking Tommaso, can we do this in the Nisq era?
Well, not yet. So this is very, 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 very important to state. I was last year at Q2B conference, the Quantum to Business conference in Silicon Valley, and I heard representatives of companies making statements, unlike what we just heard from Hartmut, which is scientifically very, very, very sound. Statements like, in 2 years, we will have quantum computers which will revolutionize the way we, synthesize drugs, okay? And then in my talk, I said, there was a lot of discussion about export control and commercial barriers. So I said, we need much less export control and we need much more hype control. Because if we say such things which have no scientific foundation, then in 2 years, then everybody will realize, and then the situation will be pretty bad. And then I have, several of these people who gave these talks coming to me afterwards and saying, that's good that you say this. And then my answer was, but why do you say that then? And then the answer often was, but we have to sex it up for our CEO. So now either the CEO is an idiot and will stay so for the foreseeable future, or within 2 years, the CEO will realize we are not having a quantum computer which, does drug design. We have to wait for longer than that. And so, yes, it's not necessary to have a fully error-corrected quantum computer, but we need substantial progress before we get there. We need many more qubits, yeah? So in this sense, the practical usefulness of the, beyond the quantum, beyond classical computing results by Google, and I am very happy that, this controversial word is no longer used by Google. I admire this and I fully support that. But the practical significance is 0 or almost 0. It can be used to certify some random numbers, but this is where the enormous importance lies. The flight of the Wright brothers, was like 12 seconds. How much was it? Less than 50 meters. I can carry anything by hand. It was completely useless to have that from any practical point of view. But we don't have to argue what it opened and what was the importance for practical technological development. So this is where we are in the Nisq era. We have to push further the boundaries. We need more than 50 qubits to do something practical, such as, for instance, those chemical reactions. We do not need hundreds of thousands, so it is going to come in the midterm, but not so quick. So this is why we need patience. This is why we need appreciation for those results which are milestones, but they are of fundamental nature. The beauty, in my opinion, the biggest beauty of Google's result is it is a fantastic result of fundamental science. And then it opens the door for what will have to come, and you need persistence. And this is what Google and other companies, and now increasingly also in Europe, companies are showing, the long-term vision to bridge that gap and to come further and achieve those applications.
Thank you for this very frank assessment, and I think it is very important to call things what they are and set expectations right. We will come back to discuss this further, but I'd like to ask first Ina another question. And what is, in your opinion, the difference between the development and commercialization of quantum computing versus classical information technologies? So I think that in your career, you have encountered the commercializations of various technologies. Are there specific challenges for quantum computing?
Well, first of all, I think quantum computing is special in the sense that it is arousing so enormous interest, despite the fact that we are very much in basic research in fundamental science to make quantum computer become real. So as Tommaso said, we also more believe on a time horizon of 10, 15 years, maybe even longer. So it's to us much open how we really going to build a practical quantum computer or a quantum computer that is going to be of practical relevance. So far we do have experimental systems, and we need to wonder what is going to be the right approach to get enough stable qubits. So when is the right point to focus on a certain technology, or how long should we be open to the various technologies that are at hand? And at the same time, it's the question how we prepare for the application of the use of the quantum computers. So how do we develop not only the new algorithms that are needed, but also how to come to the software stack needed, such that at the end, algorithms, software stacks, and the quantum computer work together and make a difference, as the theory tells us. So all this together already is a challenge, and it, so to say, also comes with the question, how do we form successful community between research and industry to make, once again, the computers real? So, and all that interests us. So what's the right approach to the ecosystem that we need for the development of practically relevant quantum computers and solutions? Because at the end, it's not about the quantum computer, it's about a quantum computer that solves problems that make a difference to all of us.
Thank you. Also, like in the field, so because we're still at in the stage of fundamental research, there's a lot of government funding, and there has been, well, to various degrees, a lot of funding to this field for 20 years now. But what we've seen I think in the past 5 years or so, it's big government initiatives such as the Quantum Flagship or the newly announced program in the US. So I would like to ask all of you to discuss a bit this government funding and how do these programs, national programs or like European programs, complement each other, and whether they are competing against each other. I guess maybe Tommaso wants to start.
Yes, well, that's a very delicate question, in the sense that my heart as a scientist resonates with what Hartmut said, which I quoted before, when he said it's a race of mankind against nature. And so we have the best chances to win this race if we cooperate as much as possible. At the same time, my sort of mind as also a European citizen, or also as a sort of an advisor to the European Commission, and also now to the German government for the big program that we are creating based on this promised 2 billion investment from Chancellor Merkel. My mind tells me, well, yes. On the other hand, we can also not be naive, in the sense that this knowledge, when it is transferred to commercialization, it also implies value creation, benefit for societies. One very extreme example, coming from physics as well, is the World Wide Web. It was created at CERN for scientific communication purposes. And CERN is a big transnational organization which, was and is devoted to fundamental science. However, the web had a lot of commercial applications, which I guess I don't have to list now. And clearly, most of the profit which came from that is not sitting in Europe, where it was created. And so I also understand very deeply the concern, which is a concern not only from the European Commission, our national governments and member states of the European Union, but as well on the side of the US, that value creation and the ecosystem which should follow from technology transfer, knowledge transfer from this field, should also have a distribution which is located in the different parts of the world which are contributing to that. And this probably means also considering this to some extent as a sovereign technology. I mentioned before the problem of export control, which is an issue which is coming at the moment mostly, not exclusively, but mostly from the United States, in which some components already for quantum computers are prevented from being exported, and so access for research groups here in Europe is limited due to this policy there. It's understandable that they do it like this. It's a hindrance for further cooperation. Is, in my opinion, something which could be overcome. It would be better to sort of build bridges rather than walls, and still we cannot do that in a fully naive way, or just thinking that all in this field is purely fundamental science, because applications are coming, will be coming, and there are, of course, economic and strategic implications which need to be taken into account. Probably, and here I'm saying something very trivial, the best model is one of co-competition, a combination of cooperation and competition. And in fact, this is how we are structuring our relationship with the US, for instance, both at the level of basic science, as well as, sort of industrial dialogue. So a combination of both aspects is probably what can bring us further while preserving everyone's legitimate interests.
Thank you. Ina, do you like to comment from your perspective?
Well, you've seen me knocking my head, so I support this view. In fact, quantum computing touches upon safety and security. So it touches upon the question, where do we put, or how do we access the question around technological sovereignty? And it is a matter of finding a good balance between cooperation and competition, and to find a good balance, how to find like-minded partners in developing this basic technology, and how to, at the end, also secure the path to commercialization. So you ask about the various programs. We are on a level playing field, so not only US, but also Europe and others invest quite a lot of research money into this important technology. And along that, we hope to develop in a cooperative manner this basic technology. And then later on, I guess one needs to see how to secure the application fields in the view of safety and security.
I see. Hartmut, can you comment on how the US Quantum Initiative is going to work together with companies like Google, IBM, or Amazon?
Of course, overall, we welcome a mix of different funding sources, because for a long-term deep tech endeavor that needs about 10 years to succeed, this is often difficult to finance entirely from private industry, because there are sort of more fickle, there are good quarters, bad quarters, startups come and go, and it's often, unfortunately, as a scientist, always hurts me to think that business-wise, it's often the better strategy to be a fast follower and only get into an area once the main technology risk has been taken out. So I'm very grateful that Google and our CEO sees it a little bit as a moral imperative to develop quantum computers for the reasons we mentioned earlier, how it could possibly help humankind address climate change. The US programs, there are manifold. One program that hasn't launched yet, but that I like a lot, we work together with Paul Debar at the Department of Energy, would use government dollars in a way that has been proven with other projects is often most fruitful, and that is to use the enormous purchasing power of government to catalyze the market. For example, there is a program, it's called the Quest program. Again, this hasn't been appropriated in Congress yet, but I hope it would happen. What it would do, it would give research dollars into the hands of researchers interested in developing quantum algorithms. And then they can use these dollars to buy quantum compute time from approved vendors. And what this would do is that would catalyze a market and reward early risk takers, and not just Google, our colleagues at IBM, INQ, Rigetti, whoever has quantum computing services to offer, can do so, and then researchers can vote with their feet where they put their money. Supposedly, they would give it to the best services, and this would catalyze the market. I think this is a very elegant way of using government funding to ensure a vibrant quantum computing marketplace early on.
Let's talk a bit more about the commercial side of things. So, of course, there are a few big players like big ventures who have been in quantum computing business for a while, and more recently, there are like I think about 100 startups that have emerged. So if I'm not mistaken, and you can correct me, like early on in the 2000s, numerous big companies, especially Japanese companies, invested in quantum computing. Their programs were discontinued or went towards other directions, and then there wasn't much happening. And I guess about 5 years or more, 5 years ago, there was a new renaissance of commercial quantum computing. I was wondering if all of you could comment on this. And my first question in this direction is, what caused this kind of evolution? The first interest that a bit died down and then was revived more recently. Maybe Tommaso, you want to start?
So why did it happen 5 years ago? I think most of this is really technological progress. It is known that in the early days of quantum mechanics, the founding fathers thought that experimenting with single quantum objects was ridiculous. Schrödinger is known having said, it would be ridiculous to imagine that you do an experiment with a single atom. This was called a Gedanken experiment, a thought experiment because of this. It would be much more reasonable to think to raise up pterodactyl in a zoo. Now, no one knows why he chose a pterodactyl, but this is what he said. And then nowadays, quantum technologies arose from the fact that people nowadays are able to manipulate individual atoms, ions, photons, individual quantum degrees of freedom in superconducting circuits in a routine way. So when this first wave, came that you mentioned before, beginning of this millennium, this was really because some individual people in some companies, had an interest. Maybe they were quantum physicists by training. They saw potential, but they were ahead of their time. So this did not have really a structural force to be carried through. So they were allowed in some niche to sort of play around because it made sense, but it was not expected to lead to some really practical development. But now what we see from companies like Google, IBM, and also Amazon is going to announce that they are going to develop their own quantum computing hardware. Yeah. So they said it just in a conference a couple of days ago. And this is an announcement which is going to come. It was a surprise also to me. So more and more are coming in a very big structural way. What was Google's motivation for doing that? Certainly Hartmut can tell us more about that, but this, as he already mentioned, came from really the top level in Google. What is the motivation by Amazon? What they said in this conference a couple of days ago was that their customers, they demand this. So this is no longer something which is a niche, and people want to use this because it is becoming practical, because it is no longer something which is a thought experiment, because the basic technology, the enabling technology, the quantum physics, being translated into quantum engineering, makes it possible to have these devices. This is the big value of Google's experiment. And this is why it was also very wise that Google, as a commercial company, in my opinion, made the right choice into focusing onto this really purely fundamental scientific question. Because showing it is possible is what is going to open the door and make it from a sort of niche curiosity to something which really has the potential to, for an industry to establish strong initiatives there. So this is what happened in the last 20 years. Slow, continuous, but enormous altogether progress in the technical capability of manipulating individual quantum systems.
I see. Ina and Hartmut, can you comment on how big companies who have obviously they have developed their hardware and they have like software on top of that to run these quantum applications, how they compete or how they complement the little startups that have appeared on the market, and how can these two coexist?
Yeah.
You
Ina, you want to go first?
Well, I can do, of course. So, good question. To start with, we think that in this very new technological field, disruptors gonna make sort of essential contribution to the development of the area. So we think about how to bring together the startups with the big companies that have the need for example, solutions to the optimization problems that I mentioned before, so in pharma industry and others. So we also consider the area to be still in the, also I said before, in the research arena, so that we discuss how we can support the development of quantum computing, and by the way, of other quantum applications for other technologies in sensing and communication and other base technologies, so that from a research and innovation perspective, we put the research money such that at the end, the quantum computer is being engineered and provided to potential users.
Hartmut?
Yeah, so of course, what we need is a vibrant ecosystem for quantum computing with various players covering aspects across the stack, from hardware to software to services. So one particular way how we cooperate with startups is there is still a scarcity of algorithms that are known or at least strongly suspected to deliver a commercial or scientific value. It would really be nice if there would be a broader portfolio of algorithms we can point to. So we try to develop some examples ourselves, but our serious software and algorithm team is not that huge. This is a few 10 people. Out there is by now probably 10,000. There are many programs, so probably 10,000 that order people knowledgeable in designing quantum algorithms. And of course, some of the best are of this work is happening in startups. For example, in where you are right now in the UK, there is a company called Facecraft, and they specialize in quantum algorithms for chemistry. And we work with such startup, in particular Facecraft, inviting them to run experiments, run algorithms on our chips and see what they get. So that is an open program we have. Any startup in the world developing quantum algorithms that writes us an email saying, hey, we have an interesting experiment, can we try it on Google's processors? We now have a quantum computing service. It's still not fully open. It's what we in an early program phase, but we have opened it to external collaborators, and they can now run algorithms on this service. And we hope that will accelerate application discoveries that way.
Seems that indeed it's very vibrant community, both the research and on the commercial front. I would like to backtrack a bit, because both Hartmut and Tommaso were talking at the beginning of quantum simulation as one of the first applications, practical applications that we're expecting in the Nisq era. And I would like, because this is a topic very close to my heart, a topic I've worked in, I can't resist but to bring it to the discussion. And I would like to ask both of you basically, what do you think could be the first quantum simulation that gives us an answer that we didn't know before, say from computing on a classical computer, or from doing actual experiments in the lab?
Well, we already have examples of quantum simulations which have achieved, results which cannot be reproduced by supercomputers, and these are, and by the way, in Germany, so the group of Emanuel Bloch in Munich, the Max Planck Institute is one of the big protagonists on the worldwide scale on this. There are, of course, other groups in the US, but among the first results in this direction, they have been obtained by him. Now, is this, an answer to a problem of which we do not know an answer? Well, actually, in many cases, it's about, calculating some dynamical properties of some Hamiltonian models. So it's kind of reproducing some calculation of some models of scientific interest. So would I call it a problem of practical interest of which we do not yet know the answer? Probably not, even though this is something which has already broader applicability in other scientific fields. And one of the fields that we see in which this is developing is applying such systems, mostly based on atoms in this case. There is also a startup in France called Pascal, which is developing quantum simulators with, at the moment, between 100 and 200 units. So the application is still to, as I said, scientific problems, but we are on the verge of going beyond that. Now, what will be the first problems? Well, probably, I guess, something along the lines of what Hartmut already mentioned. So some simulation of simple molecules, simple processes, which can have big economic impact and still cannot be simulated exactly on a classical computer. And even small molecules like methane, CH4, are good candidates for this, and cannot be fully exactly simulated on a classical computer. On the other hand, which one will be the breakthrough? I think that this is a very hot area. Google's team, as well as many other teams, as Hartmut mentioned, across Europe and across the world, are very strongly working in this direction, and many startups. And here I would rather like to resort to the sentence which is attributed to Winston Churchill or George Bernard Shaw, or you pick your favorite one, which is that, or maybe even Niels Bohr, which is that it is very difficult to make predictions, especially about the future. So I would say that the field is developing a lot, and which one will be the first, we don't know, but many people expect it will be in the chemistry of some small molecules.
Hartmut, do you agree with that?
Yeah, actually, normally I tend to agree with Tommaso, but I would maybe differ in the first part, which he said when he said, oh, there are already examples of people with quantum simulators, which are sort of special purpose devices. They are not generally programmable universal computers, but these simulators can, by the name, simulate certain aspects of quantum systems. When it said, oh, they could not have been calculated by a classical computer, frankly, I doubt this. Every time we looked, it turns out that this experimental group then didn't use the latest and greatest classical methods for quantum simulation. And if they would have spent a bit more time, they would have seen that their results were actually obtainable by classical methods. So I've yet to see an example that really stands up to, or we have computed a quantity that could not have been computed by classical machines. That being said, with the processors we have right now, we are currently running first examples of computations of quantities which indeed we do think are of scientific interest, and B, cannot be reached by classical machines. And these examples are, again, as Thomas already alluded to, they are not of commercial interest yet, but they deal with fundamental physics aspects. For example, how fast can information travel in an entangled system? You have a bunch of spins, so they have interacted with each other. Now you have entangled many-body system. And it's often also referred to as quantum chaos. People may have heard about the butterfly effect. The butterfly effect is not fully understood in the quantum world. What happens if one of those spins I ping a little bit? How quickly is this information traveling across my entangled systems? There are fundamental questions that as of today are not known. And we are putting actually finalizing touches on a paper that computes such quantities for the first time. So that may be an interesting example.
Thank you. I have I have a lot of questions for you, but I will refrain myself and just use two questions from the audience. And the first one is, what do you think, how do you assess the current positioning of the US and Europe vis-a-vis of China with respect to budgets, ecosystem, basic research, and so on? Can you, I don't know if one of you particularly wants to answer this question first, but maybe Ina, because it's just your turn.
Yeah, maybe. At least I do have some numbers on that. So already in 2018, US has set aside 1 to 2 billion for 5 years under the National Quantum Initiative Act. And as part of this initiative, the DOE introduced 5 new hubs around national labs in August this year. So the EU quantum flagship plans to spend another 1 billion euros over 10 years, plus infrastructure measures. And in Germany, we have launched a government program in also 2018 that provides 650 million euros for quantum technologies, so for more than just quantum computing by 2021 alone. And currently, along the COVID-19 situation, there has been launched a future plan, a package for another 2 billion euros for the next 5 years. So budget-wise, as I said before, we are here on a level playing field. We see strong research in all areas of the world. They differ a kind in the approaches that they use to develop the ecosystem, but I guess all share the view that, to say it again, in a fundamental research area still.
Thank you. Tommaso, would you like to add something?
Well, you asked about China, and the number you typically hear from China is like 10 billions. But whenever you ask your colleagues over there, away from a microphone or a webcam, then you hear that the reality is perhaps one order of magnitude far from that. In the sense that, there is a lot of talk about the 10 billions, but, this is not exactly what in practice one sees. And this may be part of a strategy. But I would say, again, I would support also concerning the comparison with China, what Ina said, that we are really on a level playing field. And, we are not lagging behind, so to say, in this sense, even though there may be some very bombastic announcements from China.
Thank you. The other question I want to, Hartmut, did you want to say something? Sorry to cut you.
With respect to China, actually, in terms of competition, I'm most worried about them. For example, this year we published, actually in small forums, we explained our roadmap how to get to an error-corrected quantum computer with 1,000 logical qubits, which would amount to 1 million physical qubits. And we laid out a sequence of technical milestones how to get to this goal over the course of this decade. And then it took just a few weeks that an article appeared in China, which basically was an exact copy of this roadmap, and say, oh, we are going to do this roadmap. Then IBM a little bit later followed with yet another very similar roadmap. But the ones in China I take most serious. We know those researchers. They have actually quite good teams. They are rather well funded, and I think in this race, I would take them as the most serious competitor. It is also from a general societal situation, maybe oversimplifying, but it seems like science sort of is really the new religion of China, while in other countries, unfortunately here where I'm right now in the US, the relationship to science has frayed, and that is not a good societal background for staying in the lead when it comes to innovation. So in that sense, given the enormous resources, the sheer size that China has, and their relationship to science, makes them a formidable competitor.
That's very interesting. There is a question just addressed to you, Hartmut. Will Google make an open access for quantum computing for a few number of qubits like IBM?
As I said, we have done this. We have developed this service in several years. We went through 2 internal testing phases and have now invited the first cohort of 10 external collaborators. And they are actually working with the service right now. Because they're our alpha testers, so we have to make sure the software is easy to use and they can calibrate the chips to get sort of high impact journal paper experiments out of this work. But it will open to larger and larger groups. Yes, that is our goal.
Then one last question that came from the audience, but I also had it on my list, is what are the most important challenges, and I would add the most important opportunities in the next 5 years?
Well,
I think you can, yeah, Ina, please start.
I can start. I think for the upcoming 5 years, I see the top concern in the view of the different scientific and technological challenges indeed to be the expectation management, that we master the, so to say, this topic that is in the discussion by so many stakeholders and people, to understand that is still a long way to go up until they see the real results. But it's of course huge opportunities to see the scientific development towards the practical usage at the end. So for me, it's about expectation management in long run.
Tommaso?
Well, I would say that yes. So what I call hype control is a very large challenge on the policymaking side. And then on the technical side, the challenge really is scalability. So this is why what Hartmut described, like everyone's roadmap, how to go from from the Nisq era to the error-corrected quantum computer with, many logical qubits, meaning error-corrected qubits, meaning, hundreds of thousands or millions of physical qubits. This is the big challenge. Let's not forget that, it has been an enormous achievement to get where we are with, one could say, a few dozen qubits, yeah? And still, already this quantum computer goes beyond what a classical computer can do. But it's not just a linear extrapolation. There are some very, very important challenges there, and this is the next aspect on which the future of this is going to play, and this is why this is so central in the strategy of Google and of many different countries, and it is also central in the discussion that we are carrying out in the expert body, which is advising the German government for the new initiative that we have. So this is the main point of all the discussions. This is what will decide, what is successful and who is successful in this.
Thank you. Hartmut.
Yeah, to me, the biggest challenge remains to, for the next few years, remains to find more valuable algorithms, even if we can run them today, and if they would require an error-corrected machine. If we can point to valuable applications, then it wouldn't be hard to ensure continued funding for our field. And on the hardware side, even though there are big challenges, I'm way more optimistic there. If you look historically, hardware, let's say our coherence times, the number of qubits, all these things have grown according to Moore's law type trends over the years. Algorithm development is much more serendipitous, much less planned. Suddenly a great insight comes and a new algorithm is discovered. And yeah, as I said, the better we are there, the more we can point to, the more we are assured to eventually see the big machines that require sort of reduced financing risk.
That's very interesting. Just one last question before we wrap up. So we should talk about the future. We've already talked about the challenges, and I just wanted to ask, there's another big challenge that we're all facing, not just in quantum computing, but in pretty much everything, like the economic impact of the pandemic and or like the impact on research it had. What do you feel has that? What do you feel has been the impact on quantum computing overall during this past, all the events during the past year?
Well, maybe I can start on this. So, well, obviously, on the experimental side, the lockdown, at least in Europe, has impacted, essentially everybody, and development, has been slowed down in terms of, this technical progress, which, as we repeated several times, is at the center of this field. At the same time, I would say that, on the broader scale, we see a renewed, interest and understanding from decision makers that investment in innovation and technology can really play a major role in recovery after the pandemic. And this is, for example, just a very prominent example, among the considerations which led to this big investment with 2 billion from the German federal government. So, and also I could say that in more general terms, the lessons learned from this pandemic for society, among the lessons learned on the positive side, I would say, is that there is a broader societal acknowledgement of the importance and value of sound scientific advice, sound scientific knowledge in fighting the pandemic, as well as there is a broad understanding of the effectiveness of collective action. And those are both essential elements in winning this race, all together, of course, with the different competition elements that we have, but all together in a race, as Hartmut said, I like to repeat it, mankind against nature. And I think that the support from society for this kind of action, might even have been increased in these critical times.
Thank you. I will, unfortunately, we're running out of time, and I would like to end on this actually positive note. And I'd like to say that with this panel, I learned a lot. I learned that actually, even if you have like a very realistic assessment of what quantum computing is today, you still can get very excited. Even with serious hype control, you get very excited about the future of this field. And I'm leaving this panel with a sense of optimism, and I hope you are all sharing that. So thank you. Thank you, Hartmut. Thank you, Tommaso. Thank you, Ina, for joining me today. This was a very good discussion. Thank you to our audience for engaging with us, for staying maybe for some late hour. Do continue to follow up the Falling Walls. There's a very interesting circle table following just this one on industrial AI. So stay tuned, and thank you for listening to us. Have a nice evening.
Thanks a lot. Have a nice conference.